In this second video on noncovalent interactions, we will focus on nonionic interactions and discuss how partial charges and their distribution within a molecule affects noncovalent attractions or repulsions. Both affect the size of the coulombic interactions between the partial charges. First, let's review monatomic ions. For sodium plus, for example, the charge is a full +1 located at the center of the ion because it acts as a point charge. For a polar molecule like water, it's more complicated. Where are the partial charges? Water is shown in 5 different renderings: spacefill, ball and stick, Lewis structure with lone pairs, a ball and stick with lone pairs, and the electron surface density. Now we know that oxygen-hydrogen bond is polar covalent, leaving oxygen slightly negative and each of the hydrogens slightly positive. However, the formal charge on each of these atoms is 0. But we have to consider the geometry of the molecule and think about the spatial distribution of partial charges. There is a permanent molecular dipole in water because it's a nonlinear molecule. The geometric center of slight negative is centered in the oxygen, but the geometric center of slight positive is located halfway between the slight positives on each hydrogen. One can draw a permanent dipole arrow representing this. The dipole allows water to interact with other molecules like acetone through dipole-dipole interactions, with the permanent dipole arrows aligned on each molecule to maximize attractions. Now we can add a little bit more complexity by adding the 2 lone pairs, which are visualized here in the Lewis structure in the second ball and stick model. A hydrogen bond forms between a slightly positive H on a water molecule, the H bond donor, and a lone pair on a slightly negative oxygen or hydrogen on another molecule, the H bond acceptor. By adding the lone pairs, we can account for the fact that water molecules can form hydrogen bonds to 4 other water molecules between 2 lone pair H bond acceptors and 2 slightly positive H's, H bond donors. Modern chemistry tells us where the electrons actually are, which is represented by this last rendering, showing the electron density, how the electrons and hence charges are actually distributed. The oxygen has the highest density, shown in red, and the hydrogen's the lowest, shown in blue. However, the 2 lone pairs, which look like rabbit ears on Lewis structures in the ball and stick models, are not there in our modern view. We do not need this modern view of electron density to account for hydrogen bonding in water. If we use the lone pairs, Lewis structures are sufficient. We will need electron density maps for another noncovalent interaction later. Let's make water a little bit more complicated by adding an H plus to form the hydronium ion. It's shown here in 4 different ways. Now there is just 1 lone pair on the molecule, and there is a positive formal charge on the oxygen. This might sound a little funny because we know oxygen is very electronegative and draws electrons to itself in a polar covalent bond. For an explanation, let's look at the electron density around the hydronium ion, and you'll see that the red area of highest electron density is centered around the oxygen, with a bluish green coloring showing low electron density around the hydrogens, even though that the oxygen has a +1 formal charge. This should make sense given that oxygen has more electrons and is more electronegative. Again, we don't need electron density maps, however, to account for hydrogen bonding that's observed in nature. Now we're going to see the real utility of understanding electron density maps, showing where the electrons are most likely found. Let's consider the halogen bond, a less discussed noncovalent interaction. When carbon is bonded to a halogen like chlorine or bromine, which are more electronegative than carbon, we would think that overall the halogen would be slightly negative and the carbon would be slightly positive. However, if you calculate the actual electron density around the halogen when it's bound to carbon, because it is bigger and its electrons are further away from the nucleus and more polarizable, the electron density in the halogen does get shifted toward the carbon, as shown by this enhanced red here. However, the distal end of the halogen, furthest from the carbon, is slightly positive, as shown in the electron density map, blue area right here. The slightly positive distal end of the halogen can act in a similar way to the slightly positive hydrogen on a water molecule and form a noncovalent attraction with a lone pair on a slightly negative oxygen or nitrogen on another molecule. This halogen bond is analogous to the hydrogen bond. The slightly positive end of the halogen is a halogen donor, as the slightly positive H on an oxygen is a hydrogen bond donor. The only way to understand the halogen bond is by understanding where the electrons really are, as seen in electron density maps. Finally, let's consider a nonpolar molecule like hexane that has no formal charges or permanent slight positive negative charges, so there is no permanent molecular dipole. However, given the fluctuating nature of electron clouds, at any one moment there might be a buildup of electrons on one side of the molecule and hence a depletion on the other side. This forms a temporary slight positive and negative side, and hence a temporary molecular dipole. You can imagine another hexane coming close, a hexane coming close to another hexane with a temporary dipole, inducing a temporary dipole. And the second is a slight positive on the first pulls electrons on the second toward it. This type of interaction based on temporary dipoles is called induced dipole interactions. They are also called London dispersion forces, although the word force should really not be used. Now we consider all the common noncovalent interactions. These include ion-ion or salt bridges, hydrogen bonds, halogen bonds, ion dipole, and induced dipole interactions. Based on the size of the charge and their distribution, the ion-ion is the strongest, and the induced dipole is the weakest, given similar sizes of species and distances between them. Every one of these interactions arises from the electrostatic force described by Coulomb's law, but the strength of the interaction is modified based on the presence of slight positives and slight negatives and on the distribution of those charges. The table shows their relative strengths based on the energy of the interaction. This is the directionality and this is the relative strengths. For point charges, we saw that the force between charges is proportional to 1 over r squared. You can easily show, however, that the energy, not the force in an ion interaction, is proportional to 1 over r, not 1 over r squared. We mostly use energy in kcals or kilojoules per mole in chemistry. Let's consider the energy dependency on r for each. In comparison, the covalent CH bond has a stability of about 100 kilocalories per mole. This column of relative strengths shows the energy of interaction for these different noncovalent interactions. This energy for each of these has its own dependency on R. For example, the energy for the dipole-dipole interaction is proportional to 1 over r cubed. The energy for the weakest noncovalent interaction, the induced dipole attraction, is proportional to 1 over r to the 6th. So as r increases, the energy of stabilization quickly falls off. Hopefully you now have a better understanding of the relative strengths of the noncovalent interactions and how they depend on the size of the charge and the distribution of the electrons and the distance between them. There is no hydrophobic force, but you can use the term hydrophobic interaction instead. Sometimes all of the interactions, excepting those involving ions, such as an ion-ion interaction, are collectively called van der Waals interactions. But they should not be called van der Waals forces. Likewise, it's best to use induced dipole interactions